So let's start today's proceedings. In the last class, we were talking about the physical interpretation of the Lagrangian multipliers, right? So we started with the example. So we took one nonlinear function of two variables. So the function was of x1 and x2, and we had a vector x. So f of x was the function, where our target was to maximize the numerical value for this function. And our constraint was equality constraint. So we are talking about equality constraint. So it was a circle, unit circle, with a center at 0. So it was x1 square plus x2 square equals to 1. Then for solving this system, we introduced the multiplier, Lagrange multiplier, and we've formed the new expression, which is the Lagrange expression. So we obtained a new, we can say a new function where we are trying to maximize this, okay, for different values of x1 and x2. So while we tried to form the Lagrangian, we actually did it in this way. So we took the function f of x first in the expression of L. Then we added up the Lagrangian multiplier lambda. So here it is placed as a in transpose form. As I mentioned earlier, if you have multiple expression of gx, that means if g is not a scalar expression, rather expression of vectors, g1, g2, and so on, that means if you have more than one constraints, in that case lambda would be a vector instead of a scalar. But for this example, because we have only one equality constraint, so it will remain as a scalar variable lambda. And then we have rewritten the gx in a form that gives us something like g of x equals to 0. Okay, so we can write it like 1 minus x1 square minus x2 square is equal to 0. And then we started with the graphical interpretation of the Lagrangian. What we did, we took different bounds on the values of x. Here I'm putting x and y. Simply, these are the two variables. You can simply interpret it as x1 and x2. Okay, simply x1 and x2 instead of x and y. So this is my unit circle, the green one, with unit radius in each direction. And these are the contours. Okay, contours for x square y. That is my fitness function, f of x. Now here I have put different contours. That's why I have put a constant c, arbitrary constant c. Now, can anyone tell what is the increasing direction of these contour magnitudes? I mean, is the contour increasing in this direction or in this direction? Is the contour increasing in this direction or in this direction?
First one.
First one, because it's a function of x square y. So if we move along this line, we can easily see that x is increasing in this direction. So if I move in this direction, x is increasing as well as y is increasing. So as I'm moving along in this direction, the magnitude of the contours are increasing. That means the c value is increasing. Okay. Okay. So similarly here, if I change my bound and the diagram on the right, similarly I can say that, well, x is increasing in this direction. Of course, the function is x squared. So this value would be squared. So there would be no minus sign. So that means x squared y, and y is going in the positive direction as I am moving along in this direction. So similarly here, the function contours are increasing in this direction. Okay. Now the question comes, what could be the feasible solutions? Okay. By feasible solutions, we mean that what could be your probable candidate of solutions, acceptable solutions. Okay. So because it is an equality constraint, problem, optimization problem, so I have to ensure that I have to take those points only where the g of x is exactly equal to 1. Okay. G of x is exactly equal to 1. And I'm looking for maximizing these f of x. I'm looking for maximizing this f of x. So if I just take the top expression, okay, just for the time being, if I ignore this g of x, in which direction should I move? If I go to the next diagram, in which direction should I look for the solutions? I should move along towards right, in this diagram, or in this diagram, I should go for the larger contours, okay? Contours having larger magnitude. So my intention or my inclination should be towards this direction as far as I can move, right?
Yes, sir.
As I can move. But the problem is that this is constrained, okay? I have a constraint to be fulfilled. So what is that constraint? That means this is the constraint, okay? X square plus y square equals to 1. That means I cannot select any solutions beyond this curve, okay? Beyond this green curve, any other points there, to look at all these curves, starting from here, to look at all these curves, none of the curves are actually satisfying the constraint x square plus y square equals to 1. Because beyond this green curve, beyond this point, in this zone, above this zone, anywhere, my x square plus y square is greater than 1. Okay? It is beyond the unit circle. So that means the candidate solutions can only satisfy which one? This one, okay? This could be one point. Can you see this?
Sir.
Make it a little larger, okay, a little bit clearer. Okay, my candidate solution, one candidate solution could be this one, this point, okay, where my x square y, this is the x square y equals to c contour. Any of the c values, this will satisfy. Any of these curves, any of these contours are not my candidate solutions. They are out of consideration. They are infeasible set. We call them infeasible set because they are not satisfying my equality constraint. Okay. So this could be my one solution. What are the other solutions? There is another intersection point. There is another intersection point. There is another one. There is another one. So only these points are my candidate or feasible solutions. Is that clear? Up to this point, it is clear.
Yes, sir.
Yeah, this is the way I'm picking my candidate solutions, graphically at least, graphically. So then, among all these points, among all these, because we now know, looking at the expression x square y, now we know that as I move in this direction, okay, in this curve, in this plot, as I move it from right to left, okay, which contour is the maximum? Which C value should be the maximum among this point, among this contour, and this contour, and this one?
The outer one.
This is the one, okay, where we have some tangency. You see, they are tangent, okay, they're just touching each other. Any other points there, any other points that would give me lower values of x square y. So graphically, we can identify from these contour lines of my f of x function and my circle, which is the g of x, which is the constraint function, that this is the point which should be our optimal point. Okay, this would give me a maximum value. This point would give me the maximum value of x square y, satisfying the constraints, satisfying the equality constraints. Is that clear?
Yes, sir.
Okay. Now then we said, if I look at the gradient field, okay, if I draw the gradients at this point or at this point on any of the contour lines, then at the targeted point, at the optimal point, the relationship of the gradients would be linearly dependent. Linearly dependent. What is the meaning of linear dependency? Suppose if you have two functions, okay, mathematical expressions simply, and you say they are linearly dependent, what does that mean? You have done linear algebra, right, in one of the math courses. So what does that mean? It means something like this. Let me write down some texts for you. Let's say if you have some expression, any arbitrary expression, x plus y equals to 2, okay, and then if you have some other expressions, okay, so if you have x plus y equals to 2, and let's say I just change this to, let's say, some other variables, these are two different lines. Okay, one line is x plus y equals to 2. Another straight line is z plus w equals to 4. Now, if they are linearly dependent, how do you check it? Linear dependency, or how do you express them? What is the condition of a system being linear?
If
There are
x
two.
and y are linear, so we can write them in such that ax plus by is equal to certain constant c.
Yeah, exactly. So that means you can actually relate them in a linear fashion. Okay, basically, I mean, if I talk about the mathematical jargons, then I have to say they should satisfy, that system should satisfy two conditions simultaneously. Okay, one condition is the homogeneity. What is homogeneity? One is superposition principle, another one is principle of homogeneity. Anyone recall? Can anyone recall? Okay, I think going too far. So basically, you can relate two expressions. Can you say any vectors, okay, any vectors, those, any two vectors which are linearly dependent, can you tell that somehow? How can we mention that any vector is linearly dependent or not, any two vectors? Linear algebra.
If a v equal to bu,
Sorry?
if a b equal to bu, in case that v and u are linearly dependent.
You are going into the eigenspace. Okay. Okay, you have to, I mean, check back these conditions from linear algebra. Okay. If they are linearly independent, that means they can be simply multiple. Okay, simple, you can simply put a multiplying factor for one expression and you can easily obtain the other one. Okay, that is the homogeneity condition. Okay, that is the homogeneity condition. You can simply multiply a constant or a vector of constants and you can reach at the other expression. This is the homogeneity condition. Okay. Additivity and homogeneity, if you remember. Additivity is the other name for superposition. Okay, superposition is the another name of additivity. Okay. So at the point, let's go back to our point of discussion here. So our point of discussion was, we found at least graphically a point which is our optimal for this problem. And we saw that at this point, if we look at the gradients, then they can be represented in a linearly dependent fashion. Okay. So this is where the Lagrange multiplier basically comes into action. And this is basically the next graph where I took a larger range for x from -1. X is now varying from -1 to +1. So you see x is from -1 to +1 in the x-axis. Y is similarly, probably y is from 0 to 1. So x is from -1 to +1, y is from 0 to 1. So now you have the two contours. Okay, what I have done here, simply I have taken these two, I have included, I have increased the range of x here. Okay, so that I can have this one and this one together, combined together, and I can have a single picture here. So now, if the condition is this, okay, if the condition is such that my range of x is from -1 to +1 and my range of y is from 0 to 1. So what do you think about the optimum points now? How many optimum points we may have?
2, sir.
Yeah, we can find one here as we found earlier. One is here. Okay, this is satisfying my condition. And also I can have another point here, right? Okay. So both of them, both of these points should give me the same result, same optimum result. However, the x values are different. You see, x values here are different. It is somewhere in between 0.5 and 1, plus 0.5 and 1. And here in this case, it is somewhere in between minus 0.5 and 1. Of course, the y values remain same. Okay? The y values remains same. So this is the graphical explanation basically. Now, slowly we will solve this and we will try to find out mathematically, okay, analytically, what are the exact values. So then I continued with the contours of for the gradients. I drew the gradients for the contour functions at different points. Okay, from -1 to +1, the x values were taken from -1 to +1. Then I showed the gradients for the circles. That means if I take, instead of x square plus y square equals to 1, if I make it like x square plus y square equals to any other constant c1. So in that case, how would the gradients look like? This is the case. This is used just for demonstration. Okay, our actual targeted circle is this one. Okay, which one is touching this 1 point unit circle? This one. This is our given circle or given constraint g of x. So then we combined them, combined gradients, and then we found this one. Okay, this is what is called basically linear dependency. Okay, they are not exactly equal. If you want to make them equal, then you have to multiply some scalars. Okay, this is not a vector. If this were a vector, then that would not have been, I mean, by phasor. Okay, but I'm talking about a phasor. This is not a phasor. This is a scalar. Okay, scalar value. So this is where they basically introduces the concept of Lagrangian. Okay. Now these are the, we can say, the enlarged view of this point. Okay. Probably this is the point. Okay, this is your f of x. This one is your f of x line, which is almost tangent to the circle. This is the enlarged view of the optimum point, and this is your circle. Here they're supposed to be touching. Probably my resolution of the simulation is not good enough to have the touching point. Okay, but this should be the point. I mean, here and there, somewhere here, this should be the point. So the point where the gradients, you see the gradients where the points are satisfying the optimum solution, we call it as, let's say, x1m and x2m. Okay, x1 and x2m. But in general, we also mentioned it in the last class, in general they are not exactly same. Because why? Because my expression of f and expression of g are not exactly same. Okay, so they would provide some different, it is in general, they would provide different numerical values for the gradients. Okay, so in general they are not exactly same. So to make them exactly equal, we need to introduce this Lagrangian. Okay, and at this point, both of these gradients would be parallel or anti-parallel. Okay, by anti-parallel I mean this green line could be in the reverse direction of the blue one, or vice versa. Here they are in parallel. Okay, that means lambda is positive. They have a positive dependency. However, they could also be anti-parallel. Okay. So this is the Lagrangian, which basically links up the gap between the gradient for the objective function and the gradient for the constraint function at the optimum point x1m and x2m. Okay. So here basically we stopped, and now we are in a position to actually apply this information, whatever information or knowledge we gained till now. We are in a position to apply it for our problem. So let's say the problem, we again repeat the problem here. Our problem was to maximize a fitness function x1 squared into x2 subjected to this constraint, which is rewritten here in the form of g of x equals to 0. So our first step was to define the Lagrangian. So this is what we already did earlier in one of the earlier slides. So Lx of lambda is a function of x and lambda. So you see f of x plus lambda g of x. Now the necessary condition for the maximum would be what? You simply take the gradient of this and equate them to 0, because it is a function of two different vectors. Okay, lambda could also be a vector, as I mentioned. Here it is a scalar, but it could also be a vector. So it is a function of vector x and a function of vector lambda. So you take the partial derivative or the gradients for each variable, vector of variables, and then equate them to 0. So if I calculate this, what do I get? You first take the gradient with respect to f, with respect to x. Okay. So if you take with respect to x, what do you get? You have to calculate then the gradient for this, because there's a function of x. Also, there's another portion here. Second portion is also function of x. So simply you take the gradient of the first part plus lambda is a scalar, so lambda will remain as it is. Then the gradient for the second part. Okay, and then you have to equate it to 0. So this is what you will get after you calculate this. At the same time, you have to satisfy this second condition, where we are taking the gradient with respect to lambda. So the f of x, the first part here in the Lagrangian, it doesn't contain any lambda, so that will not appear here. So only the if you take the derivative, partial derivative with respect to lambda, you will only be left with g of x. Okay, and then you have to equate it to 0. So simply the second condition gives me or takes me back to my original constraint equation. Okay, it simply returns this equation here. Okay, so then I continue with the calculation. If you calculate the gradient for f, because it is a function of two x variables, I mean x1 and x2. So if you calculate the expression f of x with respect to x1, that means it is di f of x by di x1. Okay, this is simply, you can say simply this is this portion here, it is di f over di x1, right? This one is nothing but di f over di x1, and this one should be what? What should be the expression for this one? Second one?
Del f over del x2.
Yeah, di f over del x2 or di f over di x2. Good. So this is di f over di x2. Excellent. So this is how we are going to calculate this. So it's pretty simple. You simply take this expression and you take the partial derivative with respect to your corresponding variables, respective variables. So the first one comes, you are differentiating with respect to x1. So this part has to be differentiated. 2x1, x2 remains as a constant. So 2x1, x2. Second one is di f over di x2. So simply x2 you are taking as a variable to be differentiated. So the remaining part will arrive x1 squared. Okay. Same thing you do. You take the gradients for the g function. So this is my g function. So what do you get? You take what would be this one expression for this one? The top one. Di g over di x1. Yeah, excellent. Di g over di x1. So di g over di x1. This is g. The second one would be simply di g over di x2. So in this way you can easily calculate. Okay. Now what we have to do, we have already calculated our required expressions for del fx and del gx. We know this expression, this equation has to be true. This condition has to be satisfied. So we just go in the next slide and just plug these expressions here. Okay, plug these expressions there. So after plugging in, we simply get the first two expressions. So what is the first expression? What do you get? Simply you get this. So that means this vector or matrix, whatever you say, plus lambda into this. Okay, so this plus lambda into this. So simply you would get 2x1 x2 minus lambda 2x1, that is equal to 0, and you would also get x1 square minus lambda into 2x2 equals to 0. These are the two equations coming out from the first condition here. Okay, first condition. And the other condition would simply give me back return me the constraint equation. So we would have 3 equations. Okay, 2 equations out of this, and the third equation, this one. Now, how many unknowns? We have? Do we have? Just a minute. Okay, pardon me. Just a minute. How many unknowns do you have? Okay, we have 3 unknowns. We have 3 unknowns. Okay, I'm just coming back. Okay, please allow me 1 or 2 minutes. Okay? Sorry for the interruption. In the meantime, you just go through this slide. Okay, just go through this slide. Okay, is it clear from here how the solution is coming? Any queries about this solution? So let me go through these steps. So first, from the first equation, x1, we can divide it by x1, considering x1 is not equal to 0. Okay, if x1 is not considered to be 0, then simply you can divide this expression by x1 on both sides. So then from 1 we get the relationship lambda equals to x2. Okay, lambda equals to x2. Then we use this relation in equation number 2, and we reach here x1 square is equal to 2x2 square. Okay, and then from 3, simply we use this relation x1 square is equal to 2x2 square. We plug them here in, and then we solve for x2. So x2 comes out as this. Then we simply plug them in any of the equation. So this one is the easiest one. So you simply replace it here, and you calculate x1. So you are left with this. Okay. So how many solutions do you have in total? How many feasible solutions or probable solutions do we have?
Sir, 4.
4. Exactly. We have 4. That means we have 4 combinations between these 2. Okay. Right. Now remember that our target is to maximize the function, right? Our target was to maximize the function. So if I just write my expression here, original expression here, let's check which of the solutions should be accepted by us. Okay, so I'm trying to maximize this. Okay, so can we allow any negative value of y here if I'm trying to maximize this expression? I mean by y. Okay, let me write it in terms of 1 and 2. Okay, because we have 1 and 2. x1 is for x2. This is our expression. Okay, so can we allow, or should we allow any negative value of x2 here, considering we have some positive values of x2? Because if we allow some negative values, what would happen? That would make the whole expression negative, right?
Yes, sir.
So basically what would happen, you simply discard the negative values of x2. Okay, So that means x2 can only take the values of square root of 1 by 3 because we are targeting for maximizing the function. That's why. Okay. So the negative is actually discarded. So how many solution points now would have? You would have square root of 1 by 3, only one solution for x2. However, for x1, you can allow the negative value also because we have x1 squared. Okay, so even if x1 is negative, it doesn't matter. Still, you get a positive result out of this. So the negative x2 value is discarded, and we are taking the positive values of x2. And in case of x1, we are taking both. So that means instead of 4 points, we only have 2 points, okay, to check the results. So these are the 2 points. We have square root of 2 by 3. This is the x1 value. This is the x2 value. As I said, x1 can take negative values, so it can also take minus square root of 2 by 3, whereas x2 is still the same value. Okay, so we only have 2 points, and if you calculate the function value f of x value at that point, which is x square y, you simply get this point. So now it is mathematically or analytically also it is proved that basically what we found graphically here, earlier at this point, okay, so x1 can be negative. I'm considering this is my x1 axis and this is my x2 axis. Okay, so x2 or y is positive at this point and at this point, whereas x1 can take positive, negative value as well as positive value, and this is the result. Okay, this is the optimum value for the function. So this is how we can take help of Lagrange multipliers. This is shown for an arbitrary example. Now we will shift our focus to our example of ELD, or economic load dispatch. Okay, so now let's start the ELD issue, or continue with the ELD issue. So what was the problem in the ELD? Let me reiterate that problem. So our problem was there basically to minimize the cost, right? We were targeting to minimize the cost, and we had to satisfy an equality constraint between generation and demand. If you recall, to begin with, we are ignoring any losses as well as we are ignoring the generation limits. So we only left with the generation, summation of all the generations equal to demand, and keeping this constraint in mind, we have to look out for a minimum cost solution. Okay, this was the target. So we can say this is my f of x and this is my g of x. Okay, yeah.
So I would like to ask, why have we done like the graphical representation of the gradient? Is it really needed, or you just did it to show us how things are going?
The graphical analysis?
Yeah.
No, it's not needed. It is for your understanding.
Okay, sir.
It's not mandatory. Okay, it's not mandatory, but it is mandatory for understanding. But for solving the problem, it's not mandatory. If you know the techniques, these are available anywhere in any math books or any economics book, any optimization book. You can simply apply them. But for understanding the Lagrangian, okay, understanding the Lagrangian, I actually went through all the gradient fields and other things. Okay, is that okay?
Yeah, it's okay.
Okay, thank you very much. So this is our f of x, and this is our g of x. So can anyone tell me which one is the x variables there?
Sir, PGI.
Excellent. So PGI, that means the generation output from each of the generators. We can easily treat them as our xi, x1, x2, x3, pg1, pg2 up to pgm. Okay, so this is my f of x. Here it is function of PGI. Okay, and this is my g of x. You see here also I have presence of the x variables or the PG variables. And I should write it in terms of g of x is equal to 0. So how should I rearrange this? I should rearrange this either like PD. Remember the P loss is 0, okay? P loss is 0 as mentioned here. To begin with, P loss is 0. So we only have PD here on the right hand side, and the left hand side we have summation of PGI. So simply write PD minus summation of PGI is equal to 0. This is how we are going to formulate our g of x function. So then, as we said in the optimization slide, we are going to define the Lagrangian in this fashion, same fashion, and we are going to look out for satisfying these two conditions, okay, simultaneously. This is the necessary first order optimality condition. Why it is called first order? Because we are taking the first derivative of the expression. That's why it is first order optimality condition. Similarly, you might also experience second order optimality condition. Can anyone tell any example of second order optimality condition which we have already discussed in this course? Can you recall in one of our earlier lectures?
Dissociation condition.
Sorry?
Taking the second derivative.
Second derivative, yeah. Did we take second derivative anywhere?
Or maxima and
Yes, sir.
minima.
Yeah, second derivative.
Exactly. Yeah, exactly. In the Hessian matrix, okay. In the Hessian calculation, I mean, if I want to find out whether it is a maxima or minima explicitly, then we have to go for the second order optimality condition. But here we are only taking the first partial derivative of the gradients. So this is the first order optimality condition. Okay. Okay. So now we form our Lagrangian expression. So we have, instead of using x, arbitrary variable x, I have included here PG and lambda. So the first part was, if you remember, it was f of x. So this is my f of x, summation of costs for all the generators, which are function of x variables or generation output variables, plus lambda into g of x. So you see this is represented as g of x equals to 0. So it is rewritten like PD, which was on the right hand side, was in slide number 12. You see it is written like PD minus this thing taken on this side. P losses is 0. So on the left hand side you will be left with 0. So this is f of x plus lambda of g of x. This is my Lagrangian on slide number 15. Okay. It also mentioned that there are no losses considered. If there are losses, then this expression will be a little bit slightly modified, okay, which we will take later on. So the necessary conditions, again, you have to take the partial derivatives of the gradients, you have to calculate and you have to equate them to 0. So after you calculate this, in general, this is what you get back. Okay, you have the gradient of f of x plus lambda into gradient of del g of x. This is we have already shown for the earlier example today. And the second condition always gives you back the equality constraint. G of x is equal to 0. Okay, g of x is equal to 0. So now you have to calculate this gradient of f of x and gradient of g of x. So this gradient of f of x would give you what? The gradient of f of x would give you, if you look at the function c of ci pgi, simply it would give you dci over dpgi expression. Okay, why this is such? You see, I'm not using any partial derivative di. Okay, instead I'm using the d expression. I explained it in one of the earlier classes, because you see, if in this slide, if you see in this slide number 16, C1 is a pure function of PG1. Okay, it has nothing to do with PG2. Whatever generation is provided from generator number 2, it is in no way going to affect the cost for generation 1 and vice versa. Okay, so you can say C1 is purely a function of x1, okay, considering this is my variable x1 and this is my variable x2. So these are my x variables, x1, and this is x2. So if I take the partial derivative, okay, here, in terms of, let's say, di C1 over di PG1, what will be left? The thing that would be left is simply some function of x1, okay? There is no x2. Clear?
Yes, sir.
Similarly, if I take the partial derivative, di C2 over di PG2, I'm only left with some function of PG2. So simply I can say, instead of taking a partial derivative of di C1 over di PG1, I can simply write it like dC1 over dPG1, okay? That means an ordinary differentiation, not partial differentiation. For this case, for this example of economic dispatch, that is true, okay? But may not be always true. For this one, it is true. So simply we can write it as dCi over dPgi, means I equals to 1 up to m. Yeah.
Sir, for in general condition, we have to take the partial derivative.
Yeah, the general condition I mentioned in the earlier example, because we had a multiplication of x1 and x2 there. You remember, x1 is square x2. So you had to take partial derivative because the cost function was, I mean, the variables x1 and x2 were in multiplicative form. Here they are in additive form. Okay, that's why they are not appearing in the other expression.
Yes, sir.
Okay, that was the general case. This is one specific case where you can take, instead of di, you can simply take d. Okay,
Yes, sir.
ordinary differentiation, not partial differentiation. And this del g of x would simply give you back the lambdas. Okay, if you take the derivative here, partial derivative of this expression, that means if you are going to calculate this part, okay, LPG of lambda, this is your LPG of lambda. Where is the lambda appearing? Only here. So the first part will not appear, and you will simply get back your PD minus this. This is your second condition. And if you take the partial derivative, so this one is basically this one. You are getting back your g of x, your constraint function. Then you are going to take del g of x. Why you need del g of x? Because you have to put it here. Basically, oh, this should be actually 1. Okay, there is.
You guys went out.
Yeah, yeah. So there is. Thank you for the comment. It should be 1. Okay, so it should be 1. Okay. So because you see, there is no lambda. Actually, I made a mistake. Sorry, I made a mistake here. So there is no lambda. So if you take the partial derivative only, you are going to get back the corresponding. If you take the derivative with respect to PGI, okay. So on, if you, let's say here you have PG1 plus PG2 up to PGM. If you take the partial derivative, simply you take, if you differentiate, take the derivative with respect to PG1, you will get only 1. Because of this minus, you will have a minus, okay, and so on. So that would be -1, not lambda. Okay. So then this is specific with some specific values given. So your demand now, we are going directly into problem solution. You have a demand given. You have 2 generators, so PG1 plus PG2. You have to satisfy the demand of 500 megawatt from your available 2 generating units. And for each of the generating units, you have the cost functions given in dollars per hour. So now you apply the Lagrange multiplier method. So simply you calculate whatever, I mean the theorems I have mentioned here, you simply go through those. Okay. So what we form basically this one, okay? Del f of x plus lambda del gx, okay, equals to 0. So lambda del gx is actually -1, and there is a multiplication of lambda, okay, and the dimension would be m by 1. So because you have 2 generators, you will have 2 equations. I is equal to 1 up to 2, okay. So you are going to calculate this one, and then because of the minus here, if you plug the values here, del g of x here and del f of x here, so you will get some minus sign, okay, because of this -1. So this is what I am doing. taking the partial derivative, as I said earlier, is simply taking the ordinary differentiation of this cost function with respect to PG1, and because of the minus, there is a minus lambda. That should be equated to 0. So dC1 over dPG1 is nothing but how much? 20 plus the 2 will come down here. So 0.02 minus lambda equals to 0. We take the derivative for the second one. You can easily calculate that, equate it to 0. And the third condition is coming because of this. Okay? So the first two equations are coming because of this. The third equation is coming simply the equality constraint is re-arriving here. So this is the third condition. How many unknowns? 3 unknowns. You have to calculate PG1, you have to calculate PG2, and you have to also calculate lambda. So 3 equations, 3 unknown. You can simply use the matrix formulation, which I have used here. Okay, simply use the matrix formulation. So you formulate your matrix. You take PG1, PG2, and lambda as your unknown variables. You just you fill up the matrix with the corresponding coefficients, and of course take the constant values to the other side. Okay, so the first expression you have only PG1, its coefficient is 0.02. No appearance of PG2, so it is 0. There's a 1 lambda with a minus sign, so it's -1, and so on. Okay, remember you have to take this 500 to the other side. So this is the matrix here, filled up by the constant values. And then simply you take the inverse of this, take it to the other side, and simply you get the result. Okay. Any question up to now? No question. Okay. So now let us go to a more generalized process of solving this economic dispatch problem. The process that we have shown here is easily applicable for equality constraint type problem. Okay, you will get simply linear equations, and you can simply form the matrices, and you can easily calculate the required unknown variables.
Excuse me,
Okay.
sir.
Yeah.
Sir, can you please come back to the third condition to form the third equation? Because I didn't get it. You said P.
This equation.
Yes, sir.
Okay. How is it coming?
Yes, sir.
This is nothing but this one. Okay, this one. This is the equality constraint equation. So PD is how much? 500 given. PD is how much? 500. So this is PD given. Okay.
Yes, sir.
So you have to formulate it like PD minus summation of PGs. Okay. So this is the summation of PGs. This is how it is coming. Okay.
All right, sir. Thank you very much.
Okay. So now we look and try to solve this problem. Of course, we'll take another example. But now we will be solving using another method, which is known as the lambda iteration method. Why we need it? We need it because this method is also applicable for inequality constraints. Okay. Later on, when we will incorporate inequality, by inequality I mean, let's say we incorporate the generation limits, maximum generation possible, minimum generation possible. In those cases, the solution method that we used here in this example, that is not applicable. Okay? But the one which we will start now, the lambda iteration method, because this is an iterative method, this is still, this will be still applicable for those inequality constraint problems. Okay, so it is always a good idea to have different techniques in your armory. Okay, so that you can apply it for more generalized problems. Okay. So let's go through now this process. In this case, because it is an iterative technique, what we will do, we will first assume different values of lambda here. Okay? And then we will go through very, what should I say? Very few steps. Okay? Within 1-2 steps of the algorithm. The algorithm doesn't contain very large amount of steps. Okay? Within 1 or 2 steps, we can simply solve our problem. But because it requires iteration, so that's why the name is lambda iteration. Okay? It is an iterative technique of solving the economic dispatch problem. and we are going to iterate for the values of lambda. Okay, so we are going to basically update the lambda value, and like any other iterative technique, we are going to look for some convergence. Okay, we are going to define some error function, and with the updating of lambda value, we are going to find out some diminishing value or converging value of the error. Okay, so let's see how we are going to do this in this slide. So this is in short the steps of the lambda iteration algorithm. As you can see, very few steps are required. Okay, it's not a very large or long algorithm. Computationally, it's not very involved. Okay, rather it's very simple technique. Let's go through it. So the first step is a little trivial one. You have to pick two values of lambda. Okay, two values by two values of lambda. One I'm denoting lambda L, another one is lambda H. By L I mean some lower value, H stands for some higher value. So in what respect they are lower and higher? In this respect. Okay, as I said, we are going to minimize some error function. Okay, what is the error here? What is my target? My target here is to reach or satisfy this demand. Okay, satisfy this demand with the help of my available generations. Okay, so I'm going to define my error function as this one. In this algorithm, I am going to define the error function for our problem. This is my error function. Okay, up to this point. So the difference between the generation, summation of the generation, and demand. Okay, this is my error function. I am trying to minimize this error as much as possible. Okay, the best is that exactly they are matched. This is the best possible solution. Okay, now because I don't know what would be the exact value of lambda to start with, so I have to pick two lambdas. Okay, for this algorithm I have to pick two lambdas. One lambda would satisfy this condition, the first condition here. What is the condition? That if I put that lambda value here in the expression of PG, summation of PG, and if I subtract it, if I subtract PD from that expression, then I should get some negative value. That lambda would be my lambda L. Okay, and I pick another lambda which is higher than lambda L, such that this error function becomes positive. Okay, so basically I am taking one lambda value in such a way that my error is negative, another lambda value which is giving me positive error. So what is my target? My target in the next few steps would be to go through some iterative algorithm, and try to minimize the gap between lambda L and lambda H. Are you getting my points? My target is to converge these lambda L and lambda H to such a point where this error becomes exactly zero or very negligible. This is my target. That's why I am taking values at two ends of my actual solution. Okay? My actual solution is in between lambda L and lambda H. Okay? The actual value of lambda, desired value of lambda, which would satisfy this condition, PGI, summation of PGI is equal to PD. My desired lambda would be in between lambda L and lambda H. Okay, so now let's start the algorithm. So I now check this condition. Okay, if lambda H minus lambda L, this absolute value is greater than epsilon. Epsilon is my convergence criteria or tolerance value. For any iterative algorithm, you need to define some, you can say, stopping criteria or convergence criteria. I mean, when will you stop? Okay, when would you stop? This is the stopping criteria or convergence criteria or tolerance. How much error will you tolerate? Okay, so because this is a minimization problem, we are trying to minimize this gap. So it is better to keep epsilon as small as possible for our problem. Okay. So while this condition is satisfied, you do the following. Okay, you take another, you calculate another lambda as an averaged value of the two. Okay, average value of lambda high and lambda low. You get a new lambda. Okay. Now you take this updated lambda and you plug it in your error function. This is your error function. Okay, now you plug it in the error function. So instead of putting lambda L or lambda H, you put the newly calculated lambda here, lambda M. And now you check the condition. If this new lambda gives you positive error, okay, gives you positive error, then what you do? You reduce your higher value of lambda and you set it to lambda M. Or if this condition is satisfied, the lower condition means if after putting the lambda M, the updated lambda here, after putting it into your error function, if it is still negative, that means you have to increase your lambda L to the newly calculated value of lambda M. And that ends. This is how simple it is. Okay. Just you have to check these two conditions in each iteration. At the beginning of the iteration, you have to satisfy this while condition. Now, when the algorithm will stop, when this condition is satisfied, you will end your while loop. Okay. And in between, you calculate, you update your lambda.
Sir.
Yeah.
Sir, like if the first equation is satisfied, then lambda H will be lambda M.
Yeah.
So then what will be the lambda L?
Lambda L will stay as it was in the previous iteration.
Yes, sir.
And similarly here, very good question. And similarly here, if this condition is fulfilled, lambda H will remain as it was in the previous iteration. Okay. Immediate previous iteration. Clear?
Yes, sir.
Okay, thank you. So graphically, what it is actually trying to do, let's say you have 3 generating units, okay? 3 generating units having 3 df over dp1. What is f? F is the cost function. What would be then df over dp1? Which sort of curve is this? What is the physical meaning of this? If f is the cost for generation unit 1, p is
the incremental cost curve.
Excellent. This is the incremental cost curves. Okay, incremental cost curves. So basically, what I'm trying to do, I'm trying to slide along. If let's say this is my current position. Okay, these are the incremental cost curves. Okay, incremental cost curves for my 3 generating units. What I'm trying to do, I'm going to try and slide along these lines simultaneously. Okay, simultaneously. You see, their shapes are different. Okay, their cost functions are different. That's why their incremental cost curves are also different. So I'm going to slide along these curves. At the same time, whatever generation is coming out, I'm going to sum them up and I'm going to satisfy the required demand. Okay, so when I will stop my sliding, whenever this value P1 plus P2 plus P3 is exactly equal to P demand or PR according to this diagram. Okay, so I'm going to slide. If I go up, I have to go up here also, I have to go up here also. So you see, accordingly my P1, P2, P3, they are also varying. Do you get the point? So this is the graphical explanation of the lambda iteration algorithm. Now, let's take one example, very simple example. So instead of giving you the cost functions, straightforward, in this example, they are giving you the incremental cost function, okay? So you see the cost function was something like some constant plus some other constant multiplied by PG1 plus some other constant multiplied by PG1 square, okay? It was a quadratic function. Incremental cost is simply a first order equation. It's a function of PG1. Okay, so let's consider a 3 generator system giving with information given in terms of the incremental cost function. Now you see at each equation, beside each equation, we are equating them to lambda. Why are we doing this? Anyone can answer this? And why, I mean, suddenly why we are equating them to lambda and same lambda? Did we discuss
The
this?
Lagrangian equation, the g of x equal to -1.
Yeah, excellent. So in the Lagrange, if I just go back a few slides, let me just. So this one, yeah. So you see, this one is what? This one is my incremental cost function for generation 1, generator 1. This is my incremental cost function for generator 2. And if I take this lambda to the other side, what do we get? We get the same thing. Incremental cost for generation number 1, incremental cost for generation number 2, all are equal to the single lambda. So already actually we have learned this condition, that we have to satisfy this condition, right? That's why we are directly using it for solving this problem. It is nothing new. So at the optimal point, your incremental cost for all these generations should be equal, okay? And equal to lambda variable, the Lagrangian variable. And the constraint is given in terms of P demand. So your 3 generating units should sum up and give you exactly the 1000 megawatt required. So you see that while we were talking about this algorithm, we expressed the lambdas, sorry, we expressed the PG in terms of lambda, right? So to take help from this algorithm, or to be able to use this algorithm, we have to somehow relate PGs and lambdas, right? Because PGs are a function of lambda. So keeping this in mind, we go through, we start here again, slide number 21. So what we do simply, we rearrange these expressions, okay? And we simply express PG in terms of lambda, PG2 in terms of lambda, PG3 in terms of lambda. This is what is done here, okay? There's nothing special. Just we are rewriting and representing our PGI, the desired variables, unknown variables in terms of lambda. And then what we do, it's simply iterate this lambda. We'll add PG1, PG2, PG3, and we'll check whether the demand is fulfilled or not. This is as simple as that, okay? This is where the lambda updating will be happening. Accordingly, your PG1, PG2, and PG3 will be updated. And at some point of iteration, your demand will be almost or exactly matched, depending on your tolerance value, okay? This is how the algorithm will work. So now let's pick 2 values for this example. These 20 lambda L is taken as 20, okay, which gives us lambda L20, yeah. So lambda L20 gives us this 600 minus 670, okay, minus 670. What is summation of PGI? Function of lambda. Remember, PGIs are now this. So what we have done there, we have simply put lambda equals to 20 there, okay? 20, 20, 20. And then we have subtracted 1000 from that summation, and we get some minus value. So we pick it as our lambda L. Remember, lambda L condition has to be satisfied by this expression. Okay, lambda L should be such that this error function becomes negative. Okay, so 20 satisfies this. We take it. We try lambda H, some higher value 30. It also satisfies this condition. Okay, lambda H, with this lambda H 30 equals to 30, our condition satisfies, which is greater than 0 because it is positive. So now we have got lambda L and lambda H. So we start our iteration. Okay, so for this problem, I have actually used a very small epsilon, okay, to have a good result, good, solution, good convergence. So picking this epsilon, we start the iteration. So we check this, yeah.
20 আর 30 কি randomly ধরবো?
You have to choose in such a way that this condition is fulfilled. You could take 22 and check this. You could take 28 and check this, okay?
Yes, sir.
So you can take any value which satisfies these two conditions, okay? Simultaneously. Lambda L has to be satisfied here, less than, and lambda H has to be satisfied here, okay? Then you check the first condition, lambda H minus lambda L. Remember, lambda H is 30, lambda L is 20. So of course, this is greater than, this is small value. So we calculate lambda M. So it would be 30 plus 20 divided by 2, which is 25. Then we have to use this lambda M, right? And calculate the error. This is my error. So error is what? Positive. So if error is positive, what is the condition? Lambda H has to be updated. Yeah, lambda H has to be updated. So we update lambda H. It was previously 30, so we update it to 25. Remember, lambda L should still be set at 20. Okay, it will not be updated. Again, we check lambda H is now updated to 25, lambda L is 20, this is 5, so it is still higher than my very, very small epsilon. Sorry. So yeah, we were here. So we calculate then lambda M. So we have a new lambda M. We put it into the error expression. So you get negative. Okay. So you have to update lambda L now. Lambda L was 20. So you are updating it to lambda M value 22.5. Lambda H still remains at the value equal to last iteration value. Okay, 25. Now you have to continue this until you satisfy this constraint. Okay, so maybe few more iterations. After a few more iterations, you will get these conditions satisfied. So the solution will be treated as the optimal solution with this star symbol at the as the superscript, and the lambda is found as $23.53 per megawatt hour. You just calculate PGs with this optimal lambda. Okay, you know the expressions of PGs, and these are your solutions. Okay, so this is the lambda algorithm we discussed, and this is another way to view this, because you see the lambdas were basically your lambda M value. Okay, the plot here in the x-axis is basically showing you the lambda M values. Okay, so basically what it is doing, if you check back closely at the lambda M values, it started from what? 25, right? Then it came back to 22.5, and then finally, so the final solution is in between 25 and 22.5, right?
Yes, sir.
If I again just for your interest, if I again go back, we started from 25, we jumped down to some lower value of 22.5, but after the required number of iterations, you see this result is in between those two values. So that means lambda is actually going through some oscillatory behavior. So this is what it is shown here. Okay, lambda 1, let's say this is lambda M1. For our example, it is 25. Then it jumped to some lower value, 22.5. Then it jumped to some other value. Then ultimately it will come, only 3 values are shown here, but finally it will come to such a value where your error is almost 0, right? This is the error. So error is almost 0. So lambda is basically fluctuating, oscillating from high value to low value, then jumping back to some other high value. Then probably it will move like this. If I try to draw this, it is moving like this. It is going there, it is coming here, and it will go there, come here, and finally it will, okay, it's basically going like this. So with time, okay, so the drawing is very difficult. So this is how it's going on. So finally it will come down to the optimal point. Okay, so it is actually oscillating from high value to low value, then again coming back to some other high value, then coming back to other low values, and finally it will give you the solutions. So for our example, this is what is actually happening. This is what is actually happening. Okay, so it started from some very high value of error. Okay, and then the error came down to some negative value. Remember, the first error was positive, then we came down to some negative value, and then again positive, then again negative, again positive. You see the oscillation. Finally, probably within 10 iterations, you will come to some